And today I'm going to be talking about a topic called lateral migration radiography. Also on the project, notably, is from the civil engineering department, Jerry Paris, Dr. Kyle Riding, and Dr. Christopher Ferraro, and then from our nuclear engineering department is Dr. James Boschek. So today I'm going to kind of give a overview of the technology, how it kind of evolved in our laboratory, what the state of our project is pretty early in our project, but then give some idea of where we are.
Better? Cool. So we can get into it now. When I talk about lateral migration radiography, that is a type of backscatter radiography. It's got a few differences, which I'll briefly address because that'll kind of lead into our future work. But a lot of what I will explain is just more of a traditional backscatter radiography. So the current project we are working on is investigating the use of a lateral migration radiography or backscatter radiography system to perform non-destructive analysis on crosstie materials, and particularly in the section of what's written in our contract is outside of the rail. This refers to the section both beneath where the rail runs and on the outside. Current research from our lab in the past kind of looked at the portion between the rails, had good results, and there are some commercial systems already doing that. We are also tasked with doing this for the three primary crosstie materials: wood, composite, and concrete. And we're going to be investigating image performance with different X-ray beam geometries, source detector geometries, and a few detection methods. So to give a little bit of an update, so when you think of traditional radiography, these are X-rays. When you think of that, your traditional X-ray is what we call transmission radiography. This involves an X-ray source emitting photons that pass through your target image and then are picked up by a detector on the other side of the target. These can be very powerful, would be great in the field, but you do need access to both sides of the target. So they do have some limited applications, and that's how we'll get into our talk today. So when we look at backscatter radiography, we are looking at the portions of the photons that are emitted and then scattered back from the target, and then we pick those up on the same side as our X-ray source. So we only need access to one side of the target. Generally, we get less photons through that process, but it has its applications that serve us well. A lot of this research out of our laboratory started with the shuttle program. We were tasked with doing some scans on the external fuel tank, looking for voids and delaminations in the spray foam insulation. So that was a very successful project. We still have some similar applications in research today. And these are some of the pointed out are some of the areas of particular concern, some of the attachment points and whatnot. So here is the example system built by UF for the shuttle program. This utilizes what we call a pencil beam system, which I'll go into soon, but had great success with this. The next picture should give you an example scan. That is what's called a flange ram panel. And we were able to pick up some of the notable features that we were looking on, even down to glue lines, and easily pick up voids, delaminations in that sense. So it's a very powerful technology, and it has its uses in the field, which brings us to the crosstie application. So this is another material or application where you in situ can't access the other side to place a detector on the other side of the crossties. So this is kind of previous research looking at that fan beam passing over the crossties and then being picked up by a detector within the two rails in between the gauge. So this is kind of giving, going into now my research on this current project. We have doing some calibration between all the materials to kind of allow us to move forward. So the first thing we did was construct a simulated timber crosstie. We constructed this out of MDF boards. They proved to be a pretty good calibration material for us. They have a more consistent density than some other panel products and some other wood products. So we did a series of 3/4 inch MDF boards with a CNC cut of a 1 inch by 1 inch square hole in various locations. We can also plug these holes if needed, and if we're not interested in a flaw. But this allows us to also rearrange these boards both in the XY direction, but also vertically, so we can look at the flaw depth and get images of that flaw deeper into the crosstie. Now, I did mention some transmission radiography. We have set this up in the laboratory to do transmission scans on this material. So on the left, you're looking at that 1 inch by 1 inch square flaw, and that's actually under the full depth of the crosstie. So it is a very powerful if you are able to use transmission radiography, but not practical once they're installed. But there has been some interest in this kind of use, even for crossties, as some sort of pre-installation technology to verify the quality of the crosstie. But moving forward, obviously, a lot of this project is that backscatter or lateral migration radiography. So we've been utilizing two setups of backscatter detection. On the left is what we call a pencil beam system, and this is a highly collimated version. So you take the X-ray source, highly collimated down into what we scan as a single pixel at a time. So this can then move in a snaking pattern and develop a 2D image. It's very powerful in terms of the sense you get very good resolution. The system can do millimeter to sub-millimeter resolution, but it does compromise speed as you're doing 1 pixel at a time, looking at a pixel every half to 1 second. It can obviously take a lot of time even just to scan one crosstie. But it's kind of used for us as kind of a proof of concept. So if we can get it to work on the pencil beam, then we can move forward into our fan beam setup. So our fan beam here works on similar technique, but can actually take an array of pixels at one time, thus allowing to scan at speed down a track. And that has seen some use in commercialized products. But you're going to have some trade-off in your resolution. This system here set up has a resolution of about 5 to 8 millimeters in resolution. But even though you trade off in resolution, you can actually get a slightly better image quality in a sense, as it allows more photons to pass through it because it is less collimated. So going into our timber crosstie with the pencil beam system, this is that 1 inch by 1 inch, which is a generally small flaw under what we call 3 boards. So it would be under 2 1/4 inches inside of the crosstie. So you get a decent image. You get a good look at the edges of the flaw, corners, and can really target that flaw well. But it's a long scan, and it has that trade-off that we're seeing. So once we are able to prove this concept works with the pencil beam, then we start moving into our fan beam, because that would be more able to be commercialized. So this is going to be our fan beam. We first start kind of at the surface. That's kind of our best case scenario, easy to pick up for us. So this would be that flaw at the top position, and you get a high quality image out of that. You will note that there is brighter sections in some areas, kind of off to the side of that flaw. And that's just due to the nature that there's only a detector on one side of the flaw. So you get some shadowing effects, and that's what you're seeing there. You can eliminate these shadowing effects with either a filter or putting a detector on adjacent to it, and then stitching the images together would allow you to remove that. But then the real benefit of this technology is obviously getting deeper into the flaw, seeing internal flaws. So our next image there is at 2¼ inches of depth, and still getting good resolution, good image quality out of that. We even want to move farther, getting now into what is about halfway through the depth of the crosstie, and it's getting harder to see here. You can kind of bring it out with some filtering, some contrast tools. Gets a little more difficult, but we do have also some statistical techniques to bring this out. Based on knowing, I know that the flaw is there. It is slightly darker in that area. And that's why we start to utilize gray values. We can attribute a gray value to every pixel on the image. And then if we look at the gray values in the picture, changing this can represent a flaw. So in this certain setup, a drop in your grayscale values is going to be indicative of a void. So that flaw does in fact line up with that drop in the grayscale values right there. So it's a way for us to kind of eliminate some confirmation bias when we're testing. It's pretty easy when I know where the flaw is, when I'm on my computer, to be like, okay, I see the flaw. But this gives us a kind of be able to present and give us a good representation of, yes, a flaw is located there or not. And we're kind of working, this also allows us to do some statistics. So we're working right now on some work doing a probability of detection model on something like this using grayscale values. So that's kind of moving forward in this project currently. Also written into the project was to look at concrete and composite materials. We're kind of early in both of those right now, just so far doing pencil beam on both of those. So on the left is kind of just a crude broken concrete block that we started with, taking surface scans applicable for something like center binding cracking. And then on the right, we moved into what we call a contrast tool. So these are manufactured cracks of known widths, known depths, so we can really see what the capabilities of our technology are. So going into that concrete block contrast tool, the image on top is a scan across those flaws. And then on the bottom is that matched up with its appropriate gray values. So going back to this contrast tool, the far right thickness on that crack would be 1 millimeter. On the left would be 6 millimeters in ½ millimeter increments. So we in the laboratory have been able to estimate and show detection on about the largest 8 of those cracks. So this is in development right now. We're hoping to move into more use of this pretty soon. Recently, we also have been doing some composite crosstie work. So this is an image of a spike hole on a used crosstie. So we were taking some preliminary kind of just surface scans of the spike hole to kind of verify our technology, and noticed a dark band running through that flaw that you can see on the left. So this kind of is indicative of a crack running through that location, which we were unaware of just looking at the composite tie itself. And it is actually slightly internal cracking, and it can hardly see it in this image, but the crack does run across that red line that I call out here. So this is pretty powerful to be able to see really what our hairline cracks running through these spike holes in a manner that wouldn't necessarily be possible with typical imaging techniques. Now, our project is written to look at the area of the cross tie outside of the rail, both underneath and outside. So that's kind of what we've been looking at recently. One method to do this would be kind of scanning through the steel. This definitely has its limitations, but we wanted to kind of give it a go. So this is looking at that same composite tie, that spike hole through a 1/16 inch of steel that is layered on top of it, and kind of the concept of maybe being able to scan through a tie plate or such material. This definitely has its limitations. This is only a 1/16 inch of steel, and you're already starting to lose a fair amount of image quality. And it also requires a lot more power to start going through steel out of our X-ray source. So this is definitely limited. So now what we're going to be more investigating is that lateral migration radiography and really looking at the geometry of our X-ray source and our detectors. There's a certain amount of these photons that really migrate out through the tie. So if we have our source in the center, what can we pick up on the outside of that? And that's not quite ready to be presented, a lot of it now, but we're hoping to have that coming up in the future. So that's just an overview pretty much of our technology, where it's at today. We're able to detect flaws in different materials with different techniques at depth, and preliminary investigation shows some ability to scan through steel, but with limited thickness. Our future work is then gonna focus more into that, what I've been talking about, that underneath and outside of the rail, under the tie plate area. And we have to really address steel as a limiting factor first, make sure that's not a viable option before changing up our geometry too much. We utilize a number of image assessment techniques, which are in the works right now. Some of that is being performed, and some of that work with the probability of detection model that I was talking about. And then when we move through this, we're going to be really optimizing our geometry, both of our X-ray source and our detector, and getting optimum scanning parameters, kind of our tube settings for different materials. Needed to thank our project sponsor, the FRA, as well as we've received some material acquisition support from CSX and continued lab support from LORAM. Thank you. All right. So in terms of in terms of the pencil beam, to scan a full tie with that would take hours. We generally look at sections on the order of 2 to 2 inches by 2 inches. And when you're looking at a pixel every second or so, even a scan that size can take an hour. It is more of a proof of concept technology, or if you're looking for certain hairline special application techniques. There is some current work to kind of improve pencil beam, but that's going to be a different system coming out. And then your second question was, Real wooden ties, yeah, we have done them, and we have partnered with what was G-Rex Loram to really roll out some of those systems, and they do exist. So far, I've been pretty much in the laboratory doing this, but we do have a setup in the back. We have a trailer-mounted system that can perform this over real wooden ties. You get some issues. You're not going to quite get the resolution sometimes. Looking at like a 1 inch by 1 inch flaw out of that system, but you can get general pretty good characteristics of a real tie. Yeah.
Do you believe that you can use this technology for applying quality control on the manufacturer plants?
Yeah, that's a possibility. That kind of relates in the manufacturing to more of those transmission scans. Those are a more powerful scan. So if you're looking at kind of pre-qualification, it's more viable to use more transmission because then you'll have access to put a detector on the bottom. You'll get higher quality scans out of that. So the real use of backscatter would be in the field technology. My contact information is there if you have any other questions.